Hi, my name is Guneet, and today I will be talking about a data structure called Trie. So, this was a data structure that I was researching about for a while, and I found it to be quite interesting because of how much it's used in computer science. This data structure is actually asked a lot in interviews. There are a lot of lead code questions as well related to it. Um, Basically, it's kind of used for when you're asked to find whether a string exists or not, or whether you're asked to find whether a prefix exists or not. So I have prepared a presentation and that I'll be going through in this video, and then afterwards I will also code a try from scratch, and then also implement the operations that are used on a try, which are insertion, searching, and to whether determine a prefix exists in the particular try data structure or not, which is very similar to the searching operation. Um, but so I'm just going to be sharing my presentation. I'm just trying to see whether the screen is shared or not. Yes, it's okay. So what is a trie? A trie is a tree-like data structures which is used to store a string. So the format and the structure of a trie is very similar to a regular tree. I'm not talking about a binary tree, I'm just talking about a regular tree. And most of the time it's used to store a string. But when we say string, we're not strictly just talking about letters or alphabet letters. We A string could basically be anything. It could be a sequence of special characters. It could even be a huge number, which is obviously stored as a string. So whether it's used for whether finding out whether a particular sequence of characters exist in our data structure or not, it's very efficient for that. Before I talk a little bit more about trie, I just want to show you the structure of what a trie looks like so that you can form a mental image of it. So in a trie, the root is usually empty. And then you can store characters from it. So the root is going to be empty, and then afterwards, if you want to store, for example, a string called car, you will insert a letter C and then A and then R. Now, a trie node basically consists of two things. The first thing that it consists of is the children, which could be an array of any number of pointers as you want. I wrote 26 here because I want to represent the 26 alphabets that exist, but it could be 256, it could be 200, whatever you want to prefer. And the second component that a trie node it consists of is a Boolean value that is associated with a particular array. Now, this Boolean value represents whether it's the end of the node or not. For example, if you're trying to store the word car, after you're done inserting each letter into the trie data structure, you will basically change the value of is end to true, which would mean that the word is completed, and that would also mark the ending of whether when you're trying to like search this particular word. So if I want to store the word cat, the first thing that I will look for is whether the root consists of any children with the letter C. As you can see that since I already um, constructed and inserted this word car in it, um, C already exists here. So what I'm going to do afterwards is I'm going to start from C and then I'm going to add A, T, and all into it. Just so I can show it on a whiteboard so it's easier for me to explain. Um, yeah. So the root is basically going to be empty. But then afterwards, since I want to store the word cat in it, the first thing I'm going to look for is whether the root has any children with the letter C. As you can see right now, there are no letters, no children that are associated with the root. So I'm going to add the letter C here. And then I'm going to see whether the letter A exists after C. The current node is going to be switched to here. As you can see that C doesn't has any children right now, so I'm just going to add the letter A. And then I'm going to repeat the whole process again, whether I'm going to see whether A already has a child with the letter R. As you can see right now, there are no letters associated with A right now, so I'll just add the letter R here. So what that's going to do is, after I'm done, first of all, inserting the entire word, I am going to change the Boolean value that is associated with R to true. And this would mean that it's the end of the word. Now I can insert, for example, I want to insert another word, let's say cat. I will see whether the root has any children that are the letter C. As you can see, I already have a child of the root, which is C. Okay, and then I'm gonna search for and see whether C has any child with the node A. Since that exists as well, I will then again search whether the node A has a letter associated with it, which is R. After I'm done doing that, as you can see that I don't have any letter T, which is associated with A. So I'm going to create a new node, which is going to be T. Now, as you can know in the data structure, um, so I'm just going to show the PPT later on, but this is basically how the insertion process works. Every single node here is associated with an array of 26 pointers. And again, 26 is the amount that I chose. Obviously, it can be altered as well. But they're all associated with an array of 26 pointers. And they also have the second value, which is the end of the word, which is a Boolean value which can be changed from true to false. For example, I want to insert the word camera. So I will go to C, and then I will say whether C has any children with the letter A. As you can see, it already has one, and then I will search for M. Since it doesn't has for the M one, what I'm going to do is I'm just going to create another node here with the letter M. Since this A letter has an array of 26 pointers associated to it, the letter R, the letter T, and the letter M are the values that will be added to that array. So this is how the process of insertion works. Now, obviously, R, T, and M will not be inserted in the first three places. What we usually do is that um, we kind of subtract a particular letter with the letter A, which gives us an index value. It's very similar to a lookup table where when I think of a lookup table, I think of dictionaries in Python where we have key value pairs. So we're not inserting the letter R, T, or M in the first three places, but we're actually find out the index of these letters and then we put them in those places. So we don't explicitly store these letters, but what we do is we store the indexes that we obtain after subtracting each of these values with the letter A. And yeah, so just going back to the PPT. Okay, so this is essentially the data structure of a trie. So we have a root which is empty, and then we have all of these values, which are the children of the roots. So we have C, we have B, and then after C, we also have the values that of the letters that we want to insert into a trie. So the structure of a trie is basically represented by these two values that I talked about. Again, every single node has, has basically an array of pointers or whatever value that you put here. And then we also have a Boolean value that's associated. Now, this Boolean value is very important because it represents the end of the word. As we were talking about that in that whiteboard, um, the word cam is not exactly a word. The word camera is which we inserted into a trie, but the word cam is not exactly a word because the Boolean value that is associated with it is actually false. So this is how we know whether a word exists in a trie or not by checking whether the Boolean value is set to true or not. Initially, when we create a trie, all the Boolean values are going to be defaulted to false. So it's only when we change the value to true will be um, when the word is going to be inserted into a trie. So, and then afterwards, each node represents a single character, and the root is empty, and children represent possible next characters, all the things that we went through. And the common prefixes are shared among words. As you can see, even in that example that I used, there was a letter C and A. But then I had two words that I inserted into that trie, which was cat and car. So their prefixes, CA, were common, but it was the word that was different. After we were done inserting the word car, what we did was we changed the Boolean value to true, which meant that it was the end of the word. After we inserted the word cat as well, we did the same as well, which meant that there were two words that we inserted into that particular trie. So, what are tries used for? They're used for auto completing. So, as you can, in phones, what we do is when we search for something, we just write the, two letters like CA, it automatically auto completes it with can or card, whatever your history has been. So it's very much used in those scenarios when you want to add this feature of auto completing to it. It's also used for spell checking. So we are about to spell a word, but we are not exactly sure. Um, we got the word wrong. Essentially, what the word app or any of those other softwares is going to do is it's going to assume by prefixes that that was the word that you actually meant to spell, and it will spell it for you. So it's used for spell checking as well. It's used for IP routing. It's also used for dictionary word search and prefix matching, which is something that we will be implementing here as well. And a very common question that also comes up, whether this particular prefix exists in data structure or not. And that you do that by implementing a trie. Yeah, so there are three operations that are used in a trie. There's insert, there's search, and there's start with. Insert is to add a particular word into a trie, like we did. We performed the process of insertion. There's also for searching whether a particular word exists or not. And in this operation, the Boolean value that we have in a trie comes in handy because um, it sees whether that Boolean value is turned to true or not. If it is, that means that particular word exists in a trie data structure. And then obviously there is also this operation of starts with, which is used to find out whether a particular prefix exists or not. Now, in this case scenario, all we do is we go through every single letter and we see whether those letters exist in the trie or not. What we don't do is we do not check the value of the Boolean value that we have, because in this case scenario, we don't care whether a word exists or not. We just want to see whether the prefix exists or not. So both these operations are essentially the same. The only difference is that the Boolean value is checked in the second case scenario because we want to see whether the entire word exists in a trie. But in the third one, we do not care about it. We don't check. The only thing that we check is whether the letters exist in a trie or not. Talking about performance, um, the performance is very much dependent on what you're trying to insert, what you're trying to look up. So for insertion, the time complexity is OL and L is the length of the word. So if you're trying to insert um, car, it's going to have like the complexity of like three because there are three letters that you're inserting. So it's very much ON in that case scenario. However, in the search operation, the time complexity depends on OL, which is the length of the word. Now, it's not exactly similar to ON because it does not depend on how many letters exist in a try or not. What we're seeing is whether these three words exist in a try or not. So, for example, if you're trying to look for a car, but your try has like 200 nodes, your time complexity is still going to be three because you search for three letters. So in this case, I wouldn't exactly, make it equal to ON because it does not depend on the entire try data structure, what the complexity is. And then thirdly, we have starts with, which is again dependent on what you're trying to look up. Again, it does not depend on how many nodes exist in a try data structure. What it depends on is what is the length of the prefix or what is the length of the word that you're trying to look up. So that it's very much dependent on your input. Yeah, so in terms of visualization, if you're trying to insert the word car, again the root is going to be empty, and then you will insert C, and then you will check whether C has any children or not. Since C did not have any children, you will insert the letter A. Again, you will check whether A has any children or not. It does not, so you will insert R in it. Now, if I want to insert cat, again, this is very similar to the example that I did on whiteboard, but again, the root is going to be empty since root had, so what I search for is whether the root has any child with C. Since we already inserted car, it does has a child with C. It's going to go to it. And then it's going to see whether it has a child with the node A. Since we inserted car, what you will see is that it already has a node with A in it. And then afterwards, you're again going to check whether A has any child with the letter T. Since we inserted R here, we do not have any letter with T, a node, basically a child of A, which is the letter T. So what we're going to do is, since A has two components, it has an array of pointers, and then it also has a Boolean value. What we're going to do is, after A, in one of the positions in the array, what we're going to do is we're going to insert the letter T here. And then we're going to set the Boolean value to true, which means that this entire thing is a word. Setting a Boolean value is very important because you're trying to say that CA is not a word, but it's actually CAR, which is a full word that we have inserted into the try. Again, the same thing with bar. The first thing that it's going to see is whether it has any child with the letter B. Since the root only had a child with the letter C, we're going to have to insert the letter B. And now the position of traversing has changed from root to B. So we're going to search whether it has a child with the letter A here or not. Now, we're not talking in general about whether the letter A exists in the entire try, because obviously it does with cat and car. But what we do is when we are doing the process of insertion, we have to we have to change the parent depending on how much traversing we're done with. Since we already looked for the root and it did not have the letter B here, our current position will change to B, and after which we will see whether it has a letter A or not. So since it did not have the letter A, we're going to insert A, and then afterwards we're going to see whether this particular A, not this one, since we are here, not here, whether the letter A is gonna has any children which are named R. Since it did not, we're going to insert R here. After we're done doing that, what we're going to do is we're going to set the Boolean value to true, which means that this is the end of the word. Now for the search operation, we are initially here, and then it's going to see whether it has a letter C here. Obviously it does. And then we're going to check whether C has a child with A. It does. And then we're going to see whether A has a child of T. Of course it does. And then after we're done doing that, since we are doing the search operation, not the starts with operation where we're looking for a prefix, we're going to see whether the Boolean value that is set to T is true or false. If it's true, that means that was an entire word that was inserted and this word exists in the trie data structure. But if the Boolean value is false, then that means that this is not a completed word. There are more letters or and such. So this word as it is does not exist in the trie data structure. If you're looking for bat, again, it's going to do the same thing. It's going to see whether it has the root has any child with the letter B. It does. And then it's going to see whether the letter B has a child called A. It does. And then it's going to see whether A has a child called the letter T. Since A has no further children, bad is not found. Again, we're not looking for prefixes. We're looking for, even in this case, this prefix would also not be found. But you have to check, and that's how the entire process goes. Okay, we can go to the coding part. Okay, so we are going to be implementing a trie data structure in C++. So I'm just going to include I think it's just IOStream that I'm gonna need. And then just so that's easier for me, I'm gonna do that. Okay, so I will be creating a class called trie node. And the trie node is going to have two values here. The first value is going to be an array of pointers like I talked about before. So it's going to have the same class name, and then it's going to be a pointer of the trie node, and you can basically call it anything, but I'm just going to call it children. And I'm going to put the value 26 here representing the 26 letters, but obviously it's very much dependent on you if you want to change the value or not. And then I'm going to have a Boolean value, which I'm going to say is another word. So initially what I'm going to do is I'm going to just populate these values. So I'm going to use a constructor, and then I'm going to just going to populate the values. And then the is end or world as false. So initially, all of these pointers are set to null, and this particular Boolean value is also set to false. So every single time that we are done inserting a particular word in a trie, we're going to change this Boolean value to true, which would mean that the word is completed and inserted into the trie. So I'm gonna have a class named Trie, and then it's gonna have a private member, which is gonna be the root, which is the Trie data structure. And then what we're going to do is we're going to be creating a constructor for try so that every single time that a user or whoever is basically running this program calls the try constructor, it's going to automatically create a node, a root node for it. Okay. Okay, so this is basically the structure of try. So the try node again has two components to it. First of all, we have an array of pointers. Again, I use 26 here because I wanted to represent the English alphabets, which are 26. But you can put whatever number that you want. And then the second component to a try node is the Boolean value, which we can set to true or false. Again, this Boolean value represents whether it's the end of the word or not. What I did was I just populated these values. I populated this entire array with null pointers, and then I populated this Boolean value to false. And then just created the root as a private member and also created the constructor. So every single time that a person calls this constructor, a root node is automatically created for them. Okay, we can get started with the operations. The first operation that we're going to do is insertion. So in here, I'm going to keep just one argument, which is the word that the user is going to be, that the user wants to insert into the try node. So we are going to be tracking the root. So this root, so for traversing, we're going to create a node, which is going to be the root, which we're going to use to track the position of the pointer into the entire try. And then again, a process, the things that we want to do is we want to insert. So the first thing that we're going to do is we're going to obviously use something to track where we are. The second thing that we're going to do is we're going to go through this entire word and we're going to insert letter by letter. Sorry. So we're going to be using a for loop, and here I'm just using ch just as something that we can keep track of. Now, um, the so we are inserting here. So the first thing that we're going to see is if this particular letter that we're trying to insert, now this could be, for example, bat. It could be possibility that the letter B exists in the try, but A doesn't. So whatever letter that we are at, wherever the traversing is, we're going to see whether that letter exists or not. And if it does not exist, we're going to insert it. So if current children, oh, my bad. Okay, so the first thing that we're going to do is we're going to get the index out of here. So how do we get the index of a particular letter? What we do is we basically just subtract it by A. So we're gonna get hold of the index, and then afterwards we're gonna see whether that index exists in our try or not. So we're gonna see is equal to null pointer. If it is, then We're just gonna create. Just gonna call this constructor, which is gonna create a new node for us. Okay, after we're done doing that, we are just going to traverse further. Once we have reached the end, what we're going to do is we're going to set the value of is end. Is end of word equals to true. Just so that we know that this particular word has been inserted in this. So we can try to see whether this works or not. Let me just get int main. It's gonna get try dot insert. I'm going to be converting that into an index. So how will I do that? I will take hold of that particular character and then I will subtract it by a, which will give me the index value of it. What does that mean? For example, a means 0, b means 1, c means 2. So if I subtract c by 2 by a, what I will get is I will get the index 2 value, which is where I'm going to be storing that value. So the first thing I'm going to do is I'm going to check whether um, the children, so this is the node, the root node, whether the root has any children with this particular letter. If it does not has it, what we're going to do is we're going to be creating a new node at that particular index, which would implicitly add that particular character in our trie. We're going to go through that entire same procedure. We're going to see whether it exists or not. And then afterwards, we are going to set the value of is and a word to true, which means that the word has been inserted. Similarly, we can do the search operation as well. So we're gonna store the search type to and then the first thing we're gonna do is we're gonna use something to track the current node, which is obviously gonna start from the root. And then we're gonna go through every single letter. Let's just add the value here. And then just for searching as well, you obviously need to get hold of the index. So how do we do that? We basically just subtract it by the letter A, which is 0. And then we are going to see whether that particular node where we are at has any children with that index. If it doesn't has it, then that would mean that the word does not exist. An example of that would be, for example, if you're looking for the word cat, right? So we start with the root and then we see whether the root has any child with letter C. It does. But then, for example, the trie data structure that we have basically just consists of camera. So again, we're trying to look for the word cat, but the trie data structure only contains camera. So it's gonna start at the root, it's gonna see whether the root has any child with the letter C. It does. And then it's gonna traverse to the next pointer. It's gonna see whether the C letter has any child with the letter A. It does. And then it's gonna go through this entire process again, since we're going through the entire word. It's gonna check whether the trie data structure has any letter with called T, since we're looking for the word cat. Now, A does not has any children with the letter T. And in order for there to be a word in the trie data structure, we have to ensure that every single letter is in the trie data structure. So since the letter A does not has any child with the letter T, this means the word cat does not exist. So in case we have reached this stage and we're checking every single letter, whether the next child, the next pointer that they are pointing to, whether they have the letter or not. And if it comes to that, it does not, then we're going to stop our searching operation right there and then, and we're going to return false. Now, if there is no situation like that where the root, whatever pointer that we're traversing through does not has that child, then we are going to be setting our current value to the next pointer so that it traverses. After we're done with the entire loop, what we are going to do is we're going to return the value of the Boolean pointer. Okay, so the reason that we're not returning true here is because, for example, I'm trying to think of a word, but I'm not sure if that's a word, but for example, if we're trying to look for cat, but then the trie data structure has the word cattery. So our first step would obviously be to figure out whether the trie data structure has the letters that we're trying to look for. And of course it does. It has C, it has A, and it also has T. But there is no word called cat here. The word, basically a word, is in our trie data structure if the Boolean value that is associated with the last letter is set to true or not. Since we inserted the word cadre here, not cat, the Boolean value of y would be associated with true. Basically, the end of the word is going to be set as true, which means that this t would still be set to false by default, which means the word cat does not exist here. So it's very important to notice this because um, it's as relevant to figure out whether the Boolean value is set to true as it is to figure out whether these letters exist in our trie structure or not. So this is the search operation. The only difference between the search and the prefix operation is basically prefix operation is the one where we look whether a particular prefix exists or not. What does a prefix mean? This is a prefix, for example. Cat is a prefix. Cat does exist in category as a prefix, not as a word, but as a prefix. So the only difference between the prefix operation, basically trying to find out a prefix, and a search operation is that instead of this particular statement, we would just return true. Because at this point, we don't really care whether the word exists, we just care whether these letters exist in a trident structure. And obviously, if we have gone through the entire loop, it means that the letters do exist. So we'll just return true here instead of this particular thing. Okay, testing it, we are gonna be let's do that. Let's insert something else as well. Let's insert that, for example, which we use in our presentation as well. So it's gonna search for cat, and if it's found, if the value is true, then we're just gonna say found cat, else we're just gonna say not found. We can do the entire same thing for that as well. So let's say we're trying to look for BA. We're not looking for bad, we're looking for BA. Now it's going to return as false. The reason why, it's because the letter A, the value that is associated with letter A, is the end of the word, is not set to true. It's actually set to false, which means it's not the end of the word. So this is going to return as false. So these are the two operations that we performed. The first one was to look for whether the word cat exists or not, and the second one was to look whether BA exists or not. So since we only inserted cat and bad, despite the fact that the letters BA exists in bad, this is going to return as false because the end of the word Boolean component is still set to false at A because it was not a full word. So we're gonna see it. Not sure. Um, okay, so the screen was not shared. Okay, so as you can see, the results also show that they found cat, they did not find BA, which was expected. Anyway, so this is all that I have to show for the data structure try. It was very fun to learn about it. I hope that you learned something from this video.